What's going on, everyone? Welcome back to the MLOps community. This is a very special episode we've got for you all. We've got a little bit of a lightning talk from Peeyush, who is one of the lead engineers at Chime. They are a fintech company and they're doing all kinds of use cases that deal with batch, real time, and what he calls near real time. He goes in to break down the business of what Chime is and then also really dive deep into the feature store that they set up for their real time use cases like fraud detection and monitoring solutions and how they look at monitoring, what they look at, and how they avoid alert fatigue. So, hope you enjoy this episode. It is in collaboration with our friends at Arise. If you're looking for a monitoring solution, hit them up. We'll leave a link to everything you need to know about them in the description below. And without further ado, let's hear it from Peeyush.
I'm so excited to be speaking with you on scaling real-time machine learning at Chime. So we're going to split this into three parts. Firstly, I'm going to talk about what Chime is and what we do. Then I'll talk about our very first real-time machine learning model at Chime. And finally, in the last part, I'll talk about scaling real-time machine learning at Chime. So starting with the first part, what Chime is and what we do. Chime is a fintech company, and over 75% of Americans, they rely on their next paycheck to make ends meet. Chime's mission is to help our members achieve financial peace of mind. In order to do that, Chime, in addition to providing a checking account and debit card, also provides a bunch of features. And I figured I'll mention some of my favorite ones. There's a feature called Spot Me, where Chime spots members up to $200 on debit card purchases and cash withdrawals with no overdraft fees. There's a product called Credit Builder, which is a secured credit card without any annual fees or interest that helps members build credit history. There's a feature called Pay Friends, which helps members instantly pay and receive money from friends. And there's a high yield savings account where members can save and grow their money. Next, let's talk about data science and machine learning at Chime. So our mission is to deliver machine intelligence across all our systems and products by eliminating engineering bottlenecks to individualize member experience and better inform our agent operations. Now, that's a bit mouthful, so I like to break it down into three parts. Firstly, I want to emphasize that Chime has a lot of machine learning use cases, not just personalizing member experience, which is a very common use case across the industry, but also a lot of fraud and risk related use cases like preventing fraudulent transactions, unauthorized logins, and any other fraudulent activity happening on the platform like money laundering and so forth. At the same time, we also have use cases around predicting members' lifetime value or matching them to the appropriate offers, things that we might club under the personalization category. And finally, we also have use cases when these customers are contacting us. We have thousands of agents who answer member queries on phone, on chat, and various other forums like email and so forth. And we want to personalize customer contact experience. So the goal here for the machine learning team at Chime is to deliver machine intelligence across all these systems and products, and not just to the members, but also to our agent operations team who are helping members when they face any issues. And in order to do this, we need to eliminate the engineering bottlenecks and make sure that the systems we are building can help us solve hundreds of machine learning use cases at scale. Typically, when we think about training and inference use cases at Chime, we put it in one of the three categories, and I think it's pretty common across industry. The first and probably the most common category would be batch, and training and batch inference would be some sort of like common use cases in this category. In these cases, the pipelines are operating on batches of historical data. For example, we might want to predict member lifetime value every day and or try to identify which members are likely to churn or likely to use another product that Chime offers, things like that. Some of the signs that this might be the right approach is all the data to run pipeline is available in warehouse, and we can tolerate minutes or hours of latency. And also, In the moment information has limited use. On the other extreme is the use case of real-time inference. These use cases typically require low latency inference, often less than 1 second, on events in the moment. Some examples could be, let's say, a Chime member doing a transaction at a merchant and that transaction being authorized or denied. Some signs that this is the approach that needs to be taken is low latency inference. So someone or something is blocked on prediction. For example, in the case of card swipe, uh, the merchant is waiting to see if the transaction has been approved or denied. Also, in the moment, information is vital or necessary to make that decision. So in this case, we can't make the decision until we know the merchant name, merchant category, the transaction amount, the location, whether it's online or in-store, things like that. So in the moment, information is necessary to be able to run the inference, and we cannot pre-compute and store the model output. Now, somewhere in between these two use cases, we also have a nearline inference use case. This nearline use case, it's much more common for data pipelines, but it's somewhat special and rare for when we talk about inference. Uh, One example could be, let's say a Chime member goes to the offers tab in the app and looks at different offers, and we might want to send a personalized follow-up email afterwards. So in this case, we don't need to send that email right away. So there is no low latency inference requirement. But at the same time, probably we might not want to wait for a day or 6 hours or 12 hours to send that email. So we need to trigger inference on the event happening, but we don't need the action to be happening right away. And as I mentioned, it's somewhat rare, and almost always these use cases can be either framed as batch inference use case or real-time inference use case. Now let's talk about the real-time model use case in a little bit more detail, since that's going to be the focus of this discussion. We need to take immediate action based on inference results. And as we were discussing, some examples here could be things like transaction authorization or peer-to-peer payment authorization, or when members come to the app and log in, whether to log them in successfully or whether to show a 2FA screen or whether to deny the login. Another use case could be chatbot. When members ask any questions, we can reply automatically before we escalate to a agent to help support them. In all these cases, the inference is low latency. Someone or something is blocked on the prediction. And as we were discussing for the card swipe example, in the moment information is vital or necessary, and we can't pre-compute the inference results and cache it just for serving in real time. So let's talk about the very first real-time model use case at Chime. As I was mentioning in the very first section, Chime has this feature called Pay Friends, where members can send money to each other instantly. And we see a lot of adoption and use of this feature by our members to maybe share, like give funds to their family members or to pay friends for dinner, or like things like that. But we also see a lot of bad actors who try to transfer money and to execute social engineering, account takeover, and things like that. And we wanted to use machine learning to essentially stop those bad actors from being able to use this feature to take out the money quickly. So in this case, we are using ML to identify and block these fraudulent transactions. In order to do this, we built a model inference service that's deployed on top of Chime's Kubernetes infrastructure, and it provides a HTTP API endpoint that the engineering services query. So anytime a new pay friends transaction is happening, let's say a member is trying to send money to another member, the Chime's engineering service will send a request to the model, giving details about the sender user ID, recipient user ID, the amount of money being transferred, a lot of other information like the IP addresses, things like that. We will combine this with feature information. So for example, the sender's previous interactions with Chime, direct deposits they have done, other payments transactions they have done, things like that, as well as same information for recipient, and also a lot of other information. In this case, the model uses about 200 features to to reach a decision. And this decision, it needs to be computed in hundreds of millisecond latency, because we don't want members to be waiting to know if the transaction went through or not. So the model will fetch the feature information in uh, tens of digits of millisecond latency. It will run the inference and it will respond back to the engineering service, telling whether this transaction is risky or not. At the same time, this inference service also tracks a lot of metadata out of the box. So for example, we want to track the prediction that we serve to the engineering service. We also want to track lots of metrics around the feature values, around system metrics, and things like that. And those are sent async to data streams, different data streams that are then used for monitoring, alerting, logging, things like that. Now, let's talk about the feature store component a little bit more. So we built the feature store primarily to unlock our existing bottleneck around feature lookup for real-time models. But it also helped us to reduce drift between training and inference pipelines and provided a consistent feature engineering framework that can be used by data scientists to be able to share feature definitions across different model use cases. Uh, yeah. So the Chime's feature store platform, it consists of 5 components. We have a feature registry where features are defined in feature groups. For example, there might be a feature group about a member's transaction history or about their direct deposit history and things like that. So this feature registry contains the schema of feature group as well as all the features that are part of that feature group. We have a feature computation framework which takes different data from either streams, AWS Kinesis, or from our data warehouse Snowflake, and runs computation to aggregate out the feature values. We have feature storage component, which consists of the offline feature store in S3 and feature store in online stores to be able to serve at low latency. We also have a component for feature ingestion to be able to ingest the different data that's coming in asynchronously, and the serving system that essentially reads the feature data from the online feature store and makes it available to different models for running inference. Next, let's talk about the second part of the integration for the inference service. So as I was mentioning, the inference service, it takes a request from the Chime's engineering service. It fetches the feature values, runs the inference computation, and it sends some prediction tracking and other metadata to two different data streams. So let's talk about the monitoring aspect of it. And I guess before we go in detail there, it might be useful to talk about why tracking, monitoring, auditability are important. Firstly, it enables transparency and ability to question and understand what's happening, why a particular inference was made, and what features contributed most to it. It also eases policy writers to create rules and policies on top of them. And it also might be a regulatory requirement in certain situations like lending and so on. So while we were working on the first real-time model use case, we found out that instrumentation, which essentially means being able to break down how much time is being spent where, was really helpful for us to optimize how long each inference was taking. And so instrumentation helps us track step-by-step breakdown and facilitates performance optimization. It helped us to optimize feature store call time by keeping the cache warm. We implemented heartbeat and warm caches to get the P95 latency down from 3-digit millisecond latency to 2-digit millisecond latency. It also helped us optimize our inference stack. So for example, in this case, we had a tree-based model and we were able to use Hummingbird framework to reduce the inference latency significantly. And so instrumentation was really helpful here to be able to optimize the whole inference stack end to end. In terms of monitoring, there is 4 broad categories that we typically think about. First one is system metrics. So those are metrics that the systems generate automatically. For example, as part of the managed Kubernetes infrastructure, the pods that are running, the containers that are running, their CPU memory utilization, things like that. We have operational metrics around the services that we have created, their latency or uptime, SLAs that we track, latency, things like that. We have some custom ML platform metrics that we care about around the throughput, the seasonality pattern of traffic, things like that. And we have model specific metrics around feature and model metrics. So I would like to maybe talk a little bit more about the feature and model metrics. In case of the first model that we worked on, some of the model and feature metrics that were really helpful for us were to track frequency of missing feature values, frequency of missing feature values broken down by features, model probability score distribution. So we know if the score distribution has changed significantly, then something might have gone wrong with the model. Also, changes in frequency of missing feature values by feature. So we know in case a particular feature family might not be getting ingested properly, things like that. In terms of custom ML platform metrics, some of the metrics that were really helpful for us were post API request count, so how much traffic the model service is receiving, tracking the failed count, so how many times the inference was unsuccessful because of some error that might have occurred. Also tracking the end-to-end invocation call time and average time of invocation broken down by step. So how much time is taken for getting the feature value, for running the actual inference, things like that. Now, I guess now that that was the very first real-time model use case that we deployed, and since then we have been working on scaling real-time ML at Chime. And as I was alluding to earlier, at Chime we have hundreds of places where machine learning can be useful, and we definitely want to use it there. And so this part I like to focus on how we have scaled real-time ML and tried to automate some of the work that previously was happening manually or one-off. I think the first aspect here is monitoring and alerting. Often monitoring and alerting can be an afterthought, but we wanted to have it built as part of the platform so that each new real-time model that we deploy, we get the monitoring and alerting available out of the box. Often the observability stack can be pretty hard to implement just using the UI because we have to do a lot of clicks. For example, in maybe Datadog, Arise, or any other platform that you might be using. And it can get in a state where it's very hard to track the overall state of platform. And so we try to have all of our platform, all of these stack implemented as code, and to use anomaly detection in case of monitoring metrics. So in case things go wrong, we get triggered by anomaly monitors. We also have set up standardized monitoring and alerting across ML models using infra as code, and provided metrics and dashboards out of the box to data scientists for tracking. So sort of the goal here was to make monitoring and alerting available for all models, not as an afterthought, but built into the design of the framework that data scientists use to deploy their real-time use cases to production. The second thing that we built was built tools, and the observation that gave inspiration for this project was for the very first model, there was a lot of one-off work per model deployment to production. For example, we had to understand the data scientist code implementation. We had to containerize it, write the Docker file, set it up, connection to ECR registry, set up the serving stack using Flask, implement CI/CD, monitoring, logging, things like that. And a lot of this code, it's not really model specific, but something that can be shared across models. So we implemented a pip package that's managed by the ML platform team, and it's imported by all of the models that that we are building and that we have deployed to production. And this way we are able to share the code across these model use cases and keep our model codes dry, don't repeat yourself. For example, creating inference compatible model images, HTTP request handling, things like that. Also, it introduces a more modular and structured design to model code base. We don't have to understand the data scientist code any longer. Rather, we provided pretty broad interfaces that data scientists can implement and plug into the ML platform that we have built. Also, it provides automatic logging, monitoring, and error handling for production-ready pipelines. So any errors that happen automatically get logged to Datadog. Similarly, the standard metrics, they are sent to Datadog, and we are able to support these models running in production. The third component that I would like to talk about that has helped us to scale real-time ML at Chime is the orchestration framework. And I think one way to think about it could be as the ML ops. Essentially, what we are trying to do here is be able to orchestrate different kinds of use cases that we were talking about. So batch pipelines for training or inference, or real-time serving endpoints, and be able to do it at scale. So the platform that we have built essentially gives data scientists some templates that they can use to define their pipelines for these use cases like training, batch inference, and so on. We have CI/CD set up such that as soon as their code is merged into main branch, the corresponding infrastructure is deployed in our development and production environments. And it gives us the ability to run pipelines on cron schedule. And that's essentially our take of infrastructure as code. So essentially, data scientists, they do all of their model development work in the model repo. Once they're happy with it, they're able to set up these orchestration pipelines and be able to test out the whole end-to-end implementation in more of a development environment. And then once they're ready with the testing, then we are able to promote their code base to production. I'd like to wrap up maybe by talking about some of the lessons we learned as we built our first real-time model at Chime, and as we scaled those use cases to tens of models now and hundreds in future, perhaps. Uh, Firstly, invest in building or getting a feature store. Having a real-time feature store is crucial to be able to get the information that's needed to run the inference, and investing in it will enable you to move faster towards a real-time deployment environment. Second is to build robust framework for instrumentation and load testing. It helps to see where most of the time is being spent when inferences happen. It helps us to see how much load the system can handle, and when we need to start scaling, how the auto scaling is performing, things like that. Also, monitoring data pipelines and metrics help detect issues early in the process. Thirdly, is to build monitoring and auditability in the design, as I was mentioning, and to have these more model agnostic way. That way, you'll be able to scale it much more broadly instead of just having to do this work on a per model use case, which can lead to cutting corners in case of deadlines, things like that. Fourth is to build pluggable components and open interfaces to enable to building platforms incrementally and supporting diverse use cases. For example, the build tools framework is pretty independent to the orchestration framework. And even if we have a use case that, let's say, is hard to implement in Python, and we want to implement the entire model in C++ or Java or some other framework, the orchestration framework will still be able to orchestrate those kind of models and those kind of images and things like that. So having clear interfaces between different components that are part of ML platform can help uh, keep them pluggable, be able to build on each of them incrementally, and evolve the infrastructure over time. And the last one is infrastructure as code, especially for managing infrastructure at larger scale. In our case, since we are talking about managing hundreds of models at scale, we try to have everything as code, including even the monitors, alerts, and things like that. I think a good North Star for any team that's trying to manage large number of models at scale would be to try to make easy things should be easy and hard things should be possible. And this is a quote from Larry Wall in Programming Perl.